In this example, we're going to look at applying the propagation of variances to a single derived quantity when there's a linear relationship between the quantity we're calculating and our original measurements. And to demonstrate this, we're going to use a classic surveying measurement and calculation, whereby we are going to look at a height difference from differential leveling. That's over here on the left. And we know that that height difference is calculated from a reading to a staff. That's our backside measurement. And then we also read a foresight measurement. And we know that the difference in height is the backside minus the foresight. So if we are to break this down into a linear relationship based on what we saw in the previous video and equation 5.3, we need to get this in a sort of a matrix form here. And so if we were to take that height difference, here's alpha 1 and this is alpha 2 here. And again, referring back to equation 5.3, this would be our first normal random variable or first measurement, and here's our second one here. And we know we also need to use the propagation of variances. We're going to have to come up with variance covariance matrix for X, which is going to look something like this. The variance of the foresight, the covariance of the foresight with the backside, the covariance with the foresight and the backside here again, and the variance of the foresight. I've got a small mistake here. That needs to be the backside. Okay, now because we would generally consider that we could read a staff with the same precision for both the backside and the foresight, and why wouldn't we be able to? There's no reason why reading a backside would be less precise than reading a foresight. We can assume that the variance of our sighting is the same for the backside and the foresight. And we would also be reasonably confident that there is no correlation between the backside and foresight readings, which is to say that reading the backside has no influence on our foresight reading. And so we are able to set the covariance to be 0. The readings are independent, which means we could use the shortcut formula in equation 5.3 and simply work out the variance of our change in height by applying that shortcut formula. And you can see that here, this is A1 squared by the variance of the backside, A2 squared by the variance of the foresight, which simplifies to be what we have over here on the right. Okay, so now let's actually look at applying that in with some actual numbers in Microsoft Excel and seeing what we actually get for the variance of our change in height. So let's start off with some standard deviations here for the backside and the foresight, which we know is just the same for an individual site. So we might say that we can measure the readings on our staff to plus or minus 1 millimeter as our standard deviation. Put some units in there. Now they're the same, which is what we mentioned back in the notes just before. The standard deviation of the backside and the foresight's the same, so that's pretty much the standard deviation of a sighting is equal to these two. So what we actually need for our calculations though, if we have a look back here, is we actually need the variance, which is simply the standard deviation squared. It's going to be quite a small number. And if we were using the kind of shortcut here for the sighting, since we know it's the same, it'll be the same number. Okay, so we have our variances. So we could now construct that variance covariance matrix. So we'll do it the long way to start with. So here I need the variance of the backside. We said that the observations, the backside and the foresight, are uncorrelated. So I can put a 0 here and a 0 here. And I need the variance of my foresight in this bottom right corner. Okay, that's great. And now my A matrix, well, this one's pretty easy. We saw it back here. It's just got a 1 and a -1 in it. Like so. Now, according to our rule for the propagation of variances, we're also going to need the transpose of A. So let's look to do that as well. This is a 1 by 2. The transpose will be a 2 by 1. And we'll ask Excel to do that for us. Use Control Shift Enter keys all together to fill up your matrix. Okay, so the long way round, the variance of our quantity, our delta H, so the variance of Y, which will be our delta H, our height difference, is supposed to be a matrix multiplication of, well, let's double check. The long version needs to be this propagation of variances rule here. So A by the variance of the measurements by AT. And we'll check the shortcut method gives us the same answer as well. So we need to multiply our A matrix by the multiplication of Vx by AT. Close the brackets on those. This is a 1 by 1, Control Shift Enter. So this is the variance of Y computed the long way round. And if we want the standard deviation, it would be the square root of this number, which gets us back in to meters. So that's the full long version. You could also calculate these quantities using the shortcut method shown here in the notes. We can use this shortcut here because we know that the measurements are uncorrelated. So I need to go A1 squared by my foresight variance, A2 squared by my backside variance, foresight variance. So that's simply equal to this one squared times the variance of my backside plus this one here squared times by the variance of my foresine. Oh, don't need a bracket. And of course, if I would like the standard deviation, it is again the square root of this number, which is of course exactly the same. Let's make this 4 decimal places so we can actually see the slight difference we get between our original standard deviations and the derived quantity. So there we go, there's an example with some numbers of using the propagation of variances to work out the variance and standard deviation of your derived quantity. In this case, a height difference from some leveling measurements. And we looked at how to do it the long way using the full-on matrix multiplication method and doing it with the shortcut formula we saw in the notes when we have uncorrelated measurements. So we have determined that variance down here and then the standard deviation.